Good morning and welcome to our presentation on mapping global forest change. My name is Rebecca Moore. I lead the Google Earth Engine and Earth Outreach projects at Google. Last Friday, November 15th, a paper was published in Science magazine describing the creation of the first high-resolution map of global forest cover and change. This morning, I'm honored to have with us the key representatives of the institutions involved with producing that paper and those results. We'll be sharing with you a live demonstration and a discussion. First, we'll have Tom Loveland, who is a senior scientist at the U.S. Geological Survey, Earth Resources Observation, and Science Arroyo Center. Then we'll hear from the lead author on the paper, the leader of this project, Matt Hansen, who's a scientist at the University of Maryland. Next, I will be giving a few remarks on the Google side of this. Then we'll hear from Jeff Masek, who's Landsat project scientist at NASA Goddard Space Flight Center. And finally, we'll hear from Paulina Arroyo, who's a program officer at the Gordon and Betty Moore Foundation. So without further ado, Tom, please lead us off.
Well, thank you. It's a pleasure to be here today to discuss this research on global forest change. This is work that was enabled through the generous support of the Gordon and Betty Moore Foundation, the unprecedented computing capabilities of Google Earth Engine, the stewardship of the Landsat record by the U.S. Geological Survey and NASA, and the contributions of researchers at the University of Maryland, State University of New York, Environmental Science and Forestry, South Dakota State University, and the Woods Hole Research Center. For the past 20 years, researchers have applied remote sensing using images from orbiting satellites to understand the extent and consequences of a global environmental change. Our efforts in the early years in the 1990s used 1 kilometer resolution weather satellite data to make the first map of global forest cover. In comparison to what we see today, those results are static and somewhat coarse. Today we're going to see a remarkable detailed global map of forest change produced by this multi-organization team led by Dr. Matt Hansen from the University of Maryland. The map that Matt will be introducing to us captures forest gains and losses from 2000 to 2012, and they're based on images from the Landsat program. For more than 41 years, a series of Landsat satellites have continuously imaged the Earth. Through that effort, about 4.5 million Landsat images are now archived by the U.S. Geological Survey's Arroyo Center. The Landsat 7 images that were used in this study have been capturing images of the Earth since 1999, potentially viewing the entire planet every 16 days, and capturing details of change as small as 30 meters on the ground. That's about the size of a baseball infield. The spatial detail that comes from this is sufficient to provide us with clear evidence of the ongoing changes of forest cover by humans, as well as the impacts on forests by the forces of nature. Landsat data are essential for objective assessment and for providing the evidence of what's happening anywhere in the world. The USGS makes Landsat data available to anyone, anywhere, at no cost. Researchers, decision makers, planners, and general and public citizens use Landsat in more than 180 countries on an annual basis. And they use these to monitor forests and croplands, the growth of cities, and the changes in our snow and ice fields. Because Landsat has captured transformations across the Earth since 1972, we now have what is considered to be the most comprehensive record of the planet. So today we'll focus in on changes in forest cover since 2000. Results that we'll see will improve our ability to understand the local to global implications of forest change on climate, biodiversity, and other environmental systems. Matt?
Thanks, Tom. And it's really an honor to be working with Tom Loveland, John Townsend, Chris Justice, other authors on our paper who basically founded the large area land cover monitoring discipline. And it's a pleasure to be with Tom here today and to kind of pay respect to the people who invented this field. Our work is made possible because the USGS in 2008 opened up the Landsat archive, and we could leverage all the global land cover skill that we had practiced developing with these coarser resolution data sets that Tom alluded to at the Landsat scale 30 meters. In 2008, USGS made the archive open and freely available, and we went from a cost model where at that time $600 per image. We would beg and borrow to get a few hundred images and try to do some serious work. Remember, whole PhDs were done on a single image back in the day, and that's wonderful. I mean, that's good. But when the archives open, all of a sudden you could theoretically go to 1 million images and use those in a land cover monitoring scheme. So Landsat 7 had a global acquisition strategy. The archive's open, and we can aspire to use the entire archive. That's where the high-end computing comes in. And Rebecca will talk about that. But we started practicing at national scale. How do we mine an archive to map national scale or regional and eventually global scale land cover and change? And current state of the practice, and this is a legacy of the cost model, is to work on a single image and just piecemeal together single image characterizations as Brazil maps the legal Amazon. Indonesia fights with clouds but still heads up digitizing on single images, very interactive on a single image basis. When you have the open archive, you have to automate a lot of those processes, and that's what this paper is about. It's leveraging what we did at these different national scales and trying to implement it globally using data mining algorithms for doing per pixel quality assessment. I'm getting pretty technical here, I'm sorry, but the idea is, you have to get technical to drive this automated processing to mine hundreds of thousands of images. But on the other end, we still are geographers, and we rely on image interpretation skills. We need to know what the landscape looks like. We need to know what forest distributions are, what their different densities and different landscapes are, what are the dynamics of change within them. From an image interpretation aspect, label them. We do this what we call supervised training. We train the algorithm based on examples of fire in the far north, deforestation in the Amazon. And because we process the data so consistently, we can extrapolate our algorithms, our examples, to the global scale. And that's the big deal. So when you do this work, it's important that you have geographic, ecological, even botanical background. Maybe botanical's pushing it, but you have this kind of environmental science background. But you also have to have the remote sensing skills, which is the image interpretation, data processing, and basically being able to interact with the different spectral features that are in the data. And then you have to program. Programming sets you free. If you're doing GUIs to try and do continents, it's not working. You have to program to automate the process. So we do that, and our lead on this to Peter Potapov. Peter was supposed to be here, but bad weather held him up yesterday, the tornadoes and whatnot, and he missed his connecting flight. But he built the models and implemented the algorithms at Maryland on sample data sets, and when those were finalized, he ported those to Google. And Rebecca's counterpart here, Matt Hancher, implemented those in the high performance / highly parallelized / et cetera, great high superlative computing capabilities of Google Earth Engine. And Matt Hancher could not be here because of good weather in Australia. It's too bad, but he's down in Australia. Anyway, okay, so that's the deal. So the models are built. And those models are built. They're ported to Google. We ran them twice at Google. And the second one we were happy with, just wonderful results. I'll cut out there and I'll start looking at the product, so you can go to the screen. And this is if this is not the first cloud-free image with Landsat data at the global scale, one of our other layers is, I think. I hate to say it, but all of our layers are. We're not letting bad data go through our system, and we save all of the good land observations and put those into our data mining algorithms to map forest cover and change. And like Tom said, this first theme from 2000 to 2012 is based on forest cover, and it's dynamic. So you have this pretty image of Landsat data, and our product is this. And this is an RGB where the green is tree cover, and you have different densities of tree cover. So the brighter the green it is, the denser the tree cover, 0 to 100%. And then there's loss in red, and blue is gain, and you can't see it at this scale unless you look really closely. But one of our other layers is loss by year, and you'll see much more clearly. Sorry about this. What change looks like. So I'm going to take a panorama and pan around and pan and zoom around the globe and and give you some vignettes and tell you the nature of and the quality of the product. But basically, even at a global scale, it's really quite compelling. You can see the fires in the far north, the natural systems there. You can see deforestation frontiers in the Amazon and in Southeast Asia. I'm going to go in first to one of the most intensively used landscapes in the globe, which is the subtropical domain of North America. And when you zoom in here, you start seeing the colors of change more clearly. And so just to be really careful and slow here, the greens, again, are tree cover that didn't change. The black tones are non-tree cover that didn't change. And then if you see blue, it's a tree cover gain. If you see red, it's a loss. And magenta is the mixture of both red and blue, and that's a gain and a loss at the same time. And so in this landscape, when you go across the southeast United States, and you do the area of forest over the period, the area of the land that had tree cover, over 30% of this landscape was either cleared or regrown in this period. So this is a very intensively used, it's trees as crops. You know, if you're looking for the last remaining habitat of the ivory-billed woodpecker, it's going to be a tough slog. This is very much a commoditized landscape. Turning on the loss by year, I'll zoom in here and give you another kind of aspect of the data set. So this is in the kind of lower left here is Tuscaloosa, Alabama, going up to Birmingham, Alabama. And this is the 2011 outbreak, big tornado, infamous tornado that tracked between those two cities. And we do see logging, we see fires, we see storm damage, we see disease. Anything that led to a stand replacement disturbance is documented in this data set. So we see a lot of dramatic changes. And when we do our mapping, we look for errors. And one of the errors we thought we'd found was in Sichuan, China, near the earthquake west of Chengdu. And we were trying to correct this error. It wasn't an error. It was actual forest that had slid off a mountain range, a widespread a loss of forest due to a series of landslides. And so, you know, we have to learn to trust our algorithms, I guess. So here's that's one example. Now, when we back off to look at the tropics, and this product, and I'm sorry I didn't define this. This is loss by year, and yellow tones are early in the study period. So pure yellow is 2000. As we get warmer tones, orange is in the middle, 2006, and red is 2012. And so we have this range of dynamics by year. If you look at the Amazon, and this is the arc of deforestation right here in Brazil, you see a lot of yellow tones, and that indicates that most of the change occurred in the beginning of the study period. And what we find over time in the 2000-2012 reference frame, the rate of forest loss in Brazil declined by 1,300 square kilometers per year. This is the only country with that magnitude of decrease, and it represents a concerted policy effort to slow deforestation in the Brazilian Amazon. Last Friday, they just published the new finding that the latest results are increased on an annual basis by 28%. So, you know, to highlight the kind of concerted and continuous efforts that are made to make long-lasting implementation of policies to preserve forest. If you zoom out, you see around the rest of the Amazon orange and red tones. And what we find in the tropics in general is that despite Brazil's declining rate of forest loss, countries such as Paraguay, Peru, Malaysia, Indonesia, Angola, Tanzania have increasing rates to the point that there's a statistically significant overall increase in forest loss in the tropics during this period. And so that is, you know, a bit of news that very few other countries have attempted or met with success in terms of slowing deforestation. And I zoom in here to Paraguay. Paraguay has the highest rate of forest loss on a proportional basis of any country in the globe. And the Chaco in general, the ecoregion of the Chaco that stretches from Bolivia through Paraguay into northern Argentina. Yeah, the highest rates of deforestation are in Paraguay. And the Chaco in general has, you're seeing a 20 to 30 year conversion of a natural system into agro-industry, pasture and soybean cultivation, cotton cultivation. So it's a dramatic forest transition dynamic happening. Going over to Indonesia, another hot spot. Indonesia is the bookend to Brazil, and it has the highest annual increase in forest cover loss over the study period of around 1,000 square kilometers per year. And this is coincident with, you know, in 2011 they instituted a deforestation moratorium meant to mimic in some sense the Brazilian effort. And the news in this study is that the first full year of our results inside the moratorium was the highest forest loss in Indonesia. So Indonesia has this ramping up of forest loss. a lot of our preliminary discussions were speculating there's this perverse incentive when you try to send the alarm out that there's going to be a halt to deforestation. It can actually accelerate deforestation. That's not a confirmed conclusion, but we do see here in some of this peninsular area here in Riau province in Indonesia, deep peatland soils. This is a wetland and a ring of clearing in 2012, new concessions that are being cleared. And we see this in a lot of the wetlands in Indonesia. As they've exhausted the upland resource, they're going down into the wetlands. And the patch size in the clearings of the wetlands are industrial scale, big change. Okay, so there are many vignettes that are out there. They can be used, and we want these data to be used for big science, whether it's carbon cycle or climate change modeling. But they can also be used at the local scale. We believe they have relevance there, so it's globally consistent, locally relevant. When you cut out any corner of the world, it should have some meaning. People have used our products even in small scales, such as Malawi, to relate dietary diversity to nutrition outcomes for populations. We really are eager for people to just take the data and run with it. I'm going to pass the mic to Rebecca right now, who's going to explain a little bit more of the processing of the data.
Thanks, Matt.
Thanks.
I've got to say, it's really been an honor for my team, principally Matt Hansher and David Thau, engineers on the Google Earth Engine team, to work with Matt Hansen, Peter Potopoff, Tom Loveland, the other scientists on this project, to essentially turbocharge their science for the benefit of all of us. So there's been an information gap. This is how I hear Matt Hansen talk about it, related to the state of the world's forests. The science exists, as you've just heard from Matt Hansen. The data exists, as you've heard from Tom Loveland. The Landsat data archive is a treasure trove of imagery and data going back more than 40 years. What's been a challenge, though, in putting the science together with that data at a global scale has been the scale of the data and the scale of the processing required. So when you really look at the Landsat archive, it's more than a petabyte of data. It's more than 1 billion megabytes of data. It's quadrillions of pixels. That's a lot, right? And then when you want to do the analysis on that, it can take thousands or hundreds of thousands or even millions of hours of computation to do a global scale data mining over that archive going back multiple years. And I'm not sure it's been said, but this particular product was from the year 2000 to the year 2012. So you can see, though, why with that amount of data and processing, why there never has been to date a global forest map of change going back 12 years. So back around 2008, in the lead up to the Copenhagen Climate Change Conference, Google began to be approached by scientists, by countries, by nonprofits who asked for our help in making available this Landsat data and making available scientific processing on that data. Of course, people know Google Earth and Maps. More than 1 billion people use Google Maps every week, but those are for visualization. They're not for science. So we began to put together that project, and that has led to the Google Earth Engine platform, which is, I like to say, massively parallel. Matt Hansen teases me about that, but anyway, it's a highly parallel platform for the storage and geospatial analysis of Earth observation data. And we brought in essentially the entire Landsat catalog, and working with Peter Potopoff and Matt Hansen, we brought into Google Earth Engine their models for analyzing the Landsat pixels. And then we were able to run them over 20 terapixels, 20 trillion pixels of the Landsat 7 archive from 2000 to 2012. This actually required 1 million hours of CPU processing, but because we ran it on 10,000 computers in parallel in Google data centers, we had the result in 4 days. You could do the math, you know. On a single computer, it would have taken 15 years. So we're excited that we were able to offer that kind of turbocharging to produce this unprecedented data product. The second thing that we did to help was to make this resulting science, this resulting data product, more accessible to other scientists and to the public. And that's the data portal that Matt Hansen has just been demonstrating. We encourage people to interact with that. We've tried to make it an interactive Google Maps-like interface. It even has share links. You can find a place on the planet that's of interest to you, You can produce then a link that you can share with other people. You can even embed it on your own website. The last thing I wanted to mention is that in January, we're going to make these data sets available not only for the visualization in this data portal, but also available for download. Anyone who wants to use those to produce derivative products. So again, it's been a tremendous honor for us to work with the team on this, and we hope it's just the first of many global products that are in unprecedented detail about the Earth's natural resources. Now I'm going to turn it over to Paulina Arroyo of Moore Foundation.
Thank you, Rebecca. It really is exciting to be here with you with University of Maryland, with NASA, USGS, and Google. This is one of those rare moments where we're seeing some transformational change and access to information at an unprecedented level. This is wonderful. Actually, one of the exciting elements about this effort is actually seeing Moore's Law play out. When we told our foundation's founder about this effort last week, Gordon Moore, his eyes lit up, knowing, imagining 10,000 computers processing all these satellite images and data in just 4 days. And so historically, the foundation has supported national and local research on the change in forest cover. But what we have now and what Dr. Hansen's work has done is providing a detailed global forest on the state of, in the condition of the forest at a global level. And this is very exciting for us. What we're most keen in seeing is something that Matt mentioned, is how people are going to use this information. We see this very powerful tool in engaging both from international bodies to local community groups. In fact, as we speak, the United Nations Convention on Climate Change is meeting in Poland this week. And so this is the type of information that policymakers could use to access and validate compliance with the climate change targets. NGOs can also use this to hold countries accountable for this information and for meeting those targets. Community groups can use this information to validate their work on the ground and also engage with policymakers on priorities for forest conservation. There was a question that was submitted online regarding the use of citizen science to validate this information on the ground, and we really encourage this sort of social mobilization to use this information so that community groups can work with policymakers. And finally, we really see this as an ability or enhanced ability for other researchers to use this information and go to more detailed scale and conduct other types of analysis on the drivers of deforestation, both at the local and global levels. So we've made the initial investment, or the startup cost to build this system. It's been a great engagement with Google, with all the organizations in really driving this to the level that we are now. Now we have to decide how we're going to validate this information and update it every year if possible, so that people can start using this information on a regular basis. It's also important to ask ourselves some other and more in-depth questions, like why is this happening, what can we do about it, and how can we best use this information? Dr. Hansen's work has raised the bar of transparency for accessing global information on forests. It's now our task to ensure that world leaders, conservationists actually access the information and manage the forest effectively. So we really want to thank NASA and USGS, Google and University of Maryland, and in particular Dr. Hansen for all the work that they've been doing with this effort. Thank you. And we're now going to go to Jeff, who is off-site in the NASA studio. Thanks.
Thanks, Paulina. As others have said, this is obviously a major achievement for looking at forest dynamics. I think it's also a major achievement for the Landsat program itself. If you go back to the original vision of Landsat, it was really there to establish a global monitoring capability so that you could look year in and year out at environmental changes and natural resources. And Landsat's been very successful at sort of pushing those boundaries at the national scale and even the continental scale. But Matt's work is really crossing that threshold where now we're able to do that at the global scale. And so it really sort of operationalizes the original vision of Landsat. I think if William Pecora, who was sort of the founder or the grandfather of the Landsat program, were still with us, he'd be on that stage with you in California, hanging out and with a big smile on his face. From NASA's perspective, we have a couple of areas of interest why this is particularly interesting to us. First of all, obviously we, along with USGS, build and launch the space hardware, the platforms and instruments that actually collect the data. Just in February, we launched the latest in the series of Landsat satellites, Landsat 8. It's operating successfully and collecting more data and better data than any of the previous satellites. And NASA also has a vigorous Earth science research program. And so a lot of the data mining sort of tools that Matt referred to originally have been supported in part, at least, by NASA terrestrial ecology and land use programs. And again, it's great to see that sort of prototyping work come to fruition and be applied at the global scale with the support of the Moore Foundation and Google. And so just to close on a personal note, Matt, I've known you for a long time, and I know how hard that you and Peter and your team have been working on this product. So I want to congratulate you on a job well done and for advancing the state of the research. So with that, I think we're going to be turning back over to Rebecca, if I'm correct.
Yes, thanks, Jeff. I know you're going to have to drop off, Jeff, but we are going to be moving into the live Q&A. And so there's one question that has come up that you would be in the best position to answer, which is, you mentioned a little bit about Landsat 8 and so on, but can you say a little bit more about the future of the Landsat program and other satellites that might be coming?
Sure. You know, I think Matt's work demonstrates why you want this sort of data continuity, this sort of year in, year out view of how the planet is changing. Landsat 8, as I said, is launched in February. It has a 5-year design life. We don't really know how long it's going to last. We hope it'll last a lot longer than 5 years, but there are no guarantees. So it's important to begin the planning process for the next mission after that as soon as possible. Right now, the President's budget does have a request, a line item for the next series of missions. It's called the Land Imaging Program, and the idea is to actually have an operational series of missions that last for the next 20 to 25 years. Right now, we're engaged in a series of studies to figure out what that would look like, but hopefully if you come back in a year, we're going to have a pretty concrete plan as far as how to ensure that continuity for the next couple of decades. I'll also mention that there are other international sensors out there that have characteristics very similar to Landsat, and those can be harnessed as well. In particular, we're looking at the upcoming ESA Sentinel-2 missions, which have a lot of great characteristics associated with them. And USGS and ESA are talking about how to make those data available to US users and researchers.
That would be fantastic. And you know, I've heard this project described, the current project of the Global Forest Map, as a fantastic return on investment to US taxpayers for what we've invested in the Landsat program. So here's hoping it continues going indefinitely, because we all need it. So thanks everyone, and now we're going to move to the live Q&A, taking questions that you've all submitted to the moderator forum. The first questions relate to validation of these data products. Do you have an idea or plan for validating the products using either citizen science or experts from other countries? This related question, the accuracy of this map will likely vary considerably depending upon various factors such as cloud cover. Is there data that provides information about how accuracy varies across the map? Matt Hansen, can you take that?
Sure, I'll let Paulina talk about the citizen science aspects of validation, but our formal methods for validation are design-based. They are probability-based samples of ancillary data that are used to make a statement about how accurate the map is. Depending on how many resources you have, you can disaggregate that accuracy assessment to different levels. In the paper, our accuracy numbers are at the biome scale or climate domain scale. We are moving forward with a value-added study where we're going to take 5-meter time series imagery and really get at what we consider to be a superior statement about what kind of changes in particular we're missing by looking at 5 meters compared to 30-meter data. And again, that will be able to be disaggregated to some coarser areas, but not to the level of I think the questioner's detail that this cloud-dominated area. Will we have an accuracy assessment for the coast of Gabon? We will not, but we are keen on getting you could almost say random feedback from people on the ground who live in these areas, and we've got a lot of feedback already. People telling us that this particular area is not really trees and it can't change. Other people giving us positive feedback that in fact we've mapped their agroforestry projects in a couple places in Africa and Kenya and the Democratic Republic of the Congo. So that's very positive. So that type of feedback is really important, because when we iterate on the training, on the calibration side, we can target trouble areas. We can target them and push them to give us better results. So if it's a place that we don't know we're suffering at in terms of quality, that type of feedback from experts in the field will be really useful. So I separate that kind of stuff from like our statistical design-based work, which we hold dear and we emphasize. But I'd like to give Paulina the floor.
Yeah, I think it's important to emphasize that there are already groups on the ground, community groups, education groups in places like Brazil, Colombia, parts of Africa, Asia, that are already monitoring their forests and drivers of deforestation. What would be really important is to begin to share that information and perhaps get it to the researchers, but then also in general, just share it with policymakers to vet this information. What's going to be great is now that this is accessible, you can start comparing the data that's more on the ground and collected by local communities, citizens, and so forth, but then also using the information that's already going to be online and is going to be updating regularly. So just to say that there's other groups out there who can also start collecting this information and are trained to do it, and we would strongly encourage that this continues.
And the GeoWiki idea is one of those. There's
the Institute IASA in Austria has a web-based portal, GeoWiki.com, I believe, that lets anyone look at different competing land cover products and provide information from the ground on that can help assess accuracy. All right, let's switch to two questions on agroforestry that are popular. Are there plans to map primary, secondary agroforestry and plantation forest cover separately? And does forest gain include agroforestry and plantations of mono and non-native species? Matt,
yes.
Would you like to take that?
I'd say most of our forest gain that we see in this product is for plantation forestry related. It's very intensively managed. Lower latitudes, it comes out really, really fast. That's the idea. Acacia rotations in Indonesia being 4 to 5 years. So we see that signal very clearly. Slower natural regrowth over burn scars, we see it in certain places, but we are seeing a lot of plantation dynamics. If I go to the screen, the computer screen right now, I'll zoom into what our product looks like in a heavily managed environment. So I'm zooming in here to South Africa, the border with Swaziland. And at this stage, you see a mosaic of blues, reds, and magentas. The magenta, again, is a combination of loss and gain over the study period. And so this co-located dynamic of rapid loss and gain, in addition, in proximity to isolated loss, just loss only or gain only, this is clearly forestry land use. And this is in a habitat or a natural ecosystem is typically grassland. So this is a really easy case. But the idea of mapping over time, imagine as we move forward, each grid cell on Earth has a disturbance history. And if you're looking at an acacia plantation in Indonesia, it's like clockwork. Every 5 years, the trees come and go, and they come and go, and they come and go. So this temporal domain, in addition to the co-location of the proximity of the losses and gains, we'll be able to define these forestry land uses and differentiate them from longer-lived secondary forests and primary forests. Primary forests in particular is a challenge for sure. The largest extensive primary forest, mainly in the far north and in the tropics. We are working on, well, there already is a project called the Intact Forest Landscape product that is made by Peter Potapov in our group. And we're working to extend that into the future. But the idea is, where are the forests absent of the human footprint, away from settlements, away from roads, and those things continually shrink, almost like the PROTUS data set in Brazil. As disturbance is added, these places shrink, but we infer that they are the primary forest because they don't have the real near-term human footprint.
Okay, we have a question from Jakarta. Indonesia's Ministry of Forestry disputed the findings, which again were just released on Friday in the journal Science. Indonesia's Ministry of Forestry disputed the findings, claiming the study lumps, quote, temporary deforestation, unquote, from harvest of timber plantations with loss of natural forests. Does the analysis in fact differentiate between plantation and natural forest? Matt.
Yes, our global product does not. It's just the biophysical presence or absence of tree cover, and did it experience a stand replacement recovery or reestablishment. And so when you look at a place like Indonesia, you have a lot of dynamics that are related to clearing a natural forest or clearing of timber plantations. First thing to do in Indonesia is put the official forestry land use layers on top of this data set, because there are categories of land use in the Ministry of Forestry that preclude or prohibit legally clearing. So if there's any clearing in those polygons, that's an important indicator of a loss of natural forest. In addition, in our lab, we work regionally to add more thematic richness to the data set. So instead of just tree cover, we have for Indonesia a primary forest layer that we've disaggregated this change by, and it's not in the public domain, but I would just tell you it's a substantial portion of these changes are inside primary forest, and those numbers will be quantified shortly. And but the question, narrowly speaking, is a good one. We need to bring more context to more fully explain the carbon implications, biodiversity impacts, and all that kind of thing on a region by region basis.
Tom, anything you want to add? Or?
Well, this fundamentally gets down to the definition of forest, and we can look at it from a forest cover versus a forest use perspective. This is a study looking at forest cover, in which forests are defined as lands with trees greater than 5 meters tall. That's an important definition when you're trying to understand environmental consequences of the landscape, issues related to conservation and climate change. On the other hand, forest use are lands that have the potential to grow forest. It's an economic definition more than anything else that help us understand what our economic forest industry base may be. So, I think as we study these results, it's really important to focus in on that cover term, which is what this, which is what remote sensing studies focus on.
Okay, thank you. 2 questions related to REDD, reducing emission from deforestation and degradation. So will these data suffice as inputs for REDD, measurement, reporting, and verification? And then a second question coming from Rome. Congratulations to the team, USGS and Google. Many countries face difficulties processing the data, so it's great it's done. How can countries get access? How can they be involved to help their own forest mapping and climate change actions like REDD? So can it be used for REDD, and how can countries get access to it?
Right. Does it suffice? Well, we think for sure this is the big D in REDD, the stand replacement disturbance. If you bring contextual information to it, like the primary forest, it'll serve as for establishing baseline information for a lot of countries that lack that to date. And the method can be spun forward to compare the forthcoming years to the established baseline. So that's pretty straightforward. Obviously, there's a lot more detail we need in terms of adding the second D in degradation and maybe the pools of carbon. But we think this is for the big D a really nice input. For countries themselves, we like to say that if we make a reasonable global map and we cut out any particular country and the numbers are good, if the experts in the country made their own product using our tools, they could do a better job because they know the landscape that much better, and they can tease out that little bit much more information out of the algorithm. And our algorithm by definition has to find all these dynamics, treat them the same, and there's a little bit of compromise in there. What we don't like is that if everybody breaks out their own little patch of the globe and they use slightly different methods, and then when you get a synthesis up at the global scale, it doesn't make sense. So there's a little bit of tension there. But we definitely advocate local experts who know their countries to use these type of tools to replicate our system.
Yeah, and I would just add that one of the reasons Google got involved in this to begin with is that some of the developing world countries, tropical forest countries, approached us and said, one of them said, our computers are 12 years old, how are we going to be able to do this ourselves? And so that's one of the reasons we built Earth Engine and partnered with University of Maryland and USGS and so on. So this data will be available to all the countries in January and can be used as a starting point in their own tools, or in fact in Google Earth Engine. We're already working with a number of countries who are using Earth Engine as a tool to create their own forest cover maps. And again, this is a great input to that. Okay, next. How do you tell the difference between nature-induced forest loss and human-caused forest loss?
You know it when you see it. No, kidding. We are working on attribution. So you have this, there's a lot of ancillary thematic information we need to bring. We already talked about, what was it that was cleared? Was it primary, secondary? Was it a plantation type of a forest? This is what's the approximate cause. What was the source of the removal? And so we're working on attribution based on spectral and spatial features to disaggregate loss due to fire, loss due to mechanical removal, loss due to storms, and loss due to disease. And once we do that, the carbon implications are very different, the land use implications are very different, and so we're working on that. And you can see it, you know when you see a fire, and we're gonna attach each of these polygons of change with an approximate driver of the change.
Okay. Decision trees were used, this is coming from Berlin, decision trees were used for cloud shadow screening and change mapping. How far are these models region specific? Did you use regional, continental, and or global models?
So our QA model was global except above 60 degrees north, where the SRTM DEM it was used to help us with QA, especially for shadow. So we built a different model above 60 degrees latitude north. So we had two models for QA, and QA was about finding clouds, haze, shadow, and water, and we have different states, and we filter the data based on those states. For the characterization work, just because of data handling and that idea of our image interpretation mode and iteration of the products, we worked at a continental scale. So each of the big continents were divided, and we made separate models. That's listed in the supplementary material. We applied them per continent.
Perfect. Can you elaborate a little more on how far your Earth Engine code had to consider partitioning data or space into tile sections? How far Earth Engine does this for you? Yes, as I mentioned during our part of the talk, because the models that were developed at the University of Maryland by Matt Hansen and Peter Potapov run at the pixel level, we could, in practice, split up all of the Landsat pixels and run those models on different computers. We would split up into tiles of 256 by 256 and farm those out to, we farmed it out to 10,000 computers in parallel. Earth Engine handles all that for you under the covers of the API. So any scientist who brings their models into the Earth Engine platform has access to that massively parallel computation that does it, farms it out to different computers, and then gathers all the results and stitches it all back into the seamless global mosaic. Okay, what are the plans you have for this data set in the long haul? Will it become a standard product like those NASA releases for MODIS on a regular basis, which has resulted in massive standard use of the processed products? Maybe Tom, would you comment on that?
Yeah.
Could this become a standard product?
That is our interest. One of the reasons the USGS is actively involved in working with Matt in this is that we do see a strong need to provide annual updates on forest cover change or land cover change in general at a global scale. This is work that's the first step in that process, and it gives us a starting point now to understand the science quality of the results and the steps needed to make this an ongoing, into the future, repeatable process. And so we are working toward that.
And I would just add that Landsat 8 makes it easier. You have two Landsats.
Yep.
One's got it missing scanline corrector malfunction. This idea of two, maybe three, the more you have, the more rapid you can update and produce coherent products at a global scale. So an annual update for forest dynamics is aspirational. I think it can be done.
And perhaps just to add that from our perspective, the Moore Foundation also working with governments for the policy and how this information can both validate global, but then at the national levels, working with countries in the Amazon in particular and other places, validating that information and having the policymakers use that information is going to be really key. That's one of our main interests as well.
Okay, here's another. From Vagan University, it seems USGS allows you to have an exclusive data pipeline, Matt, to Landsat data. How can scientists without this privilege reproduce your results? So do you think that's in fact a fair question?
to me. I think these results are replicable. There is no getting around. We have this issue in Africa. We've got to dump 10,000 images on a Ministry of Forestry, for example. That's not the objective, really, because the data handling is huge. Are you ready to handle 1 million images? Right. This is a total. So, I think that to be critical of the USGS data policy, man, there's no critique coming from us. They set the standard for open, free access with FTP links and everything that just work. There are no barriers to the data that I can tell, that I can see, but I'd let Tom riff on it a little bit.
Yeah, and I guess just to be perfectly clear, the USGS Landsat data policy calls for all Landsat data, that's 4.5 million images in our archive, to be available to anyone on a non-discriminatory basis anywhere in the world. Now, there are different sizes and types of Landsat users, some that may need a dozen images on an annual basis, and others that need almost 1 million, or maybe 4.5 million images. And we will work with all users to make sure they have access to the archive, and that through our internet download processes they can grab what they need. So anybody can work with us to make sure they get the data that are required.
And just on the Google side, we've created essentially a mirror online archive of the data, working with USGS. Thank you, Tom. To make it all available. So there's no restrictions. Everyone has access to it. All right. The product mainly used Landsat 7 data, and Landsat 7 data starting from 2003 suffering from the scanline error. How certain is your approach to filling correcting this error? We can still see some of this artifact even after filling data gaps.
Yes. Good eyes. No, you have less. The scanline gaps don't move that much. So by definition, in certain parts of the world, it's gonna affect product quality. But in the general processing scheme, we treat it like a cloud. It's just missing data, and we keep going forward. And we know how many good looks we have per pixel globally. And when you look at just our data counts or data richness, those gaps come through. They don't limit our characterization in most instances, but they do in others. And that's why having a couple up at the same time, Landsat 8 is gonna improve greatly our quality. And I would say, it's interesting to think about inter-sensor calibration, maybe like Sentinel, Landsat, even working with multiple Landsats. They're each one is a little different. They each have little different characteristics. These gaps are a big deal, but they didn't preclude us from making this model. And when we attribute error, maybe we'll be able to quantify the contribution of the gaps to our error.
Can I add a comment to that? One might wonder why Landsat 5 data, for example, were not used in this study, since for a considerable part of the record they overlapped. And of course the issue is that you need complete global coverage, and the ability to have global coverage was only affordable, or only technically possible, starting with the launch of Landsat 7. Partly due to technical reasons with Landsat 7 or 5 mission, but also because Landsat 7 has a long-term acquisition practice that ensures that we will get seasonal coverage of the entire global landmass throughout each year, every year. So this is the source that had the data we needed.
Yeah, it's the only one that could do it.
Okay. Here's a couple related questions. This is from Washington, D.C. We work to help foreign aid organizations map their work. It would be useful to incorporate this data as an overlay on their maps. We already use Google Maps as our base map. Is there an API for adding this layer to an existing map? Also another one from Cambridge in the UK. Great work. How and or where does one download and or access localized copies of these data sets for further investigation? So there is a download link that's on the data portal. You can click on that and express your interest in having access to the data. We plan to make it available in January 2014, and so you'll be notified if you express interest there. I'm sure the word will also get out. And as far as an API, yes, you would be able to use standard Google Maps API when that data is made public to put that as an overlay on your own custom maps. All right. Here's another one that maybe is repetitive of a previous question, but would you consider changing forest loss to overstory change? much presented as forest loss, is actually a sustainably managed, regenerating young forest. Validity is compromised by the forest loss label. Young forests are still forests. Maybe again there's a bit of confusion between forest cover and land use, but yes?
Yeah, again, this goes back to the definition of what was mapped in this study, and that's trees greater than 5 meters tall. If we look at the southeastern United States, for example, there will be a harvest of a pine plantation followed by a relatively quick replanting of that land. Now, it's going to take 2 to 3 years before that land goes from the saplings that are put in the ground to that 5-meter height. And so, eventually, as we monitor forest cover, it will become a gain. But when we are below that 5-meter level, as consistently as possible, it's a non-forest.
Mm-hmm. Yeah. This is it's a semantic tug of war between different groups, and the easiest way to distinguish it is forest cover versus forest land use. And we say forest change, we define it in the context of cover. Some of the more belabored kind of versions are very hard to pithily use. Overstory canopy, about it gets really
This
long.
is just simply a biophysical reality of the forest
That's what
on
it is.
Earth,
Yeah.
right?
Mm-hmm.
Very,
story.
very simple.
Trees
Okay.
are no trees.
That's it.
Okay.
And yeah.
Let's
you'll see
move
it
to
in the
a
data.
totally different kind of question. The current mapping is on a Mercator projection of the planet that distorts area at higher latitudes. Will this data become available as a KMZ to run on Google Earth's 3D terrain platform? So, as you can imagine, we would all love to see this forest cover and forest change data draped over the globe. We've actually already done some internal experiments at Google, which I would like to show you guys maybe later today. And eventually, yes, we would certainly like to make that available to the public as well, because it's a very compelling way to experience the data.
I would just say lat long is the most user-friendly. The geographic is just user-friendly for people to just incorporate into their studies, so that's why we went with it.
Okay, here's one I don't know if anyone can answer. Maybe we'll throw it to Moore Foundation. How will improved remote sensing technology affect prices for land use carbon markets? Will improved tech increase access to markets for low-income communities? Do you want to try that? Anyone want to try that?
No.
Hard question. Well, I don't know if there would be really effect in the price of the carbon. I don't know if there would be a link with that. But I would assume that if we make the technology more massive, it would actually be low cost. And the fact that we are having this accessible on a free basis, and as of January, you can actually download the data, I would think that would drive other prices down in any case. And I'm not sure about the carbon link if with that. It could possibly make it better to measure carbon eventually, but I think we're still too soon to really say anything about that.
Okay. So there's a lot of congratulations to the team in here, but maybe just end with one last question. Is this a new paradigm for processing Landsat scale Earth observation data now that Landsat and soon Sentinel data are freely available, i.e. moving away from the per scene pretty picture analysis? And will other data streams be incorporated?
Sure, 100%. That's what we've always said. We think that the path row should be a thing of the past. That was always the atomic unit of our studies, and we had to buy them and strategize over using these path rows. Now, most users should not be aware at all that there is a path row system. We should process the data so that it's seamless. You get your area that you're interested in a time series and the product, and you have no idea about the way it was acquired. And this should work, globally and locally. When the data are delivered, and we do this with developing countries, we do this with like 5 countries right now. We put all the data on a server. They pan around a seamless picture of their country and map the country in a week on a server. Google Earth Engine, the similar thing. It's using a remote access to the archive to do the same thing. But again, you have this clean data, and you have no idea whatsoever about the blockiness of this acquisition. It's immaterial.
It's all just pixels.
Pixels.
And on that note, I'd like to thank everyone, Matt, Tom, Paulina. This is the conclusion of our program. Thanks very much.